Okay, so today we're going to talk about multiplying and dividing rational expressions. Up to this point, we've been dealing with graphing rational functions on your x and y coordinate plane and looking at very simple rational functions as well as more general rational functions. So today we're going to get into rational expressions and the operations that go along with these rational expressions. So before we start, a couple key pieces of information that we want to make sure we're all on the same page with is a rational expression is in simplified form provided its numerator and denominator have no common factors. So rational expression is in simplified form if your numerator and denominator have no common factors. So an example of this, a very general example of this, is given to you in the table below. If you have a situation where A times C is being divided by B times C, since C is your common factor, we can divide those out, cancel them out, and we're left with A over B. An example of this could be 6 divided by 4, okay? If we look at this more closely, 6 broken down into its basic terms is 2 times 3, and 4 broken down into its basic terms is 2 times 2. Since 2 is your common factor in both of them, we can simplify it to be 3 over 2. So that's basically what we're doing. We're taking these old algebra key concepts that you learned years and years ago, and we're just going to apply them on a bigger scale, okay? So simplifying a rational expression usually requires 2 steps, and I outlined those 2 steps for you on this sheet of paper. You're not always going to have these 2 steps in front of you, so it's going to be really important for you to kind of memorize what these 2 steps are. So step number 1, factor the numerator and denominator. That will always be step number 1. If you factor them right off the bat and you get them into smaller groups, it'll be very obvious most times what your common factors are. Step 2 has you dividing out any factors that are common to both the numerator and denominator. Okay, so I'm giving you an example here that we're going to talk about it before we move on to actual full-blown examples where we're going to be simplifying them a little bit more. So in this example, we have x squared plus 5x all divided by x squared. Just like we did in the table above, we're going to factor out what they have in common. So let's do your numerator first. So in your numerator, we're not looking at the denominator, so just in the numerator, we have the x squared plus 5x. In both of these terms, we have x present. So I'm going to pull x out in front. If I pull x out of both terms, that means I have 1 x left over in this first term plus 5 left over in my second term. When I write it this way and I pull that x out, just know that they're attached through multiplication, okay? Once I factor as small as I possibly can my numerator, I now can factor and simplify my denominator. In my denominator, I just have x squared. X squared in its most basic terms, just like we did up above, is x times x. In this case, because they're attached through multiplication, the first x and your second x, well, the first x in the numerator, the first x in the denominator can cancel out. They're common terms. So x plus 5 remains in my numerator, and x belongs in my denominator. I just want to make sure I point out these 2 x's can cancel because you have them attached to their numerator and denominators through multiplication. In this final answer down at the bottom, these 2 x's cannot cancel because the top x is attached to the 5 through addition. The only time you guys can cancel is if they are attached through multiplication. So these 2 x's do not cancel, and your final answer is x plus 5 divided by x. So let's look at example 1. Example 1 has us simplifying this rational expression. So going back to our 2 steps, the first step is to factor the numerator and denominator, and more importantly, we're going to start focusing on the numerator. It's usually just the easier to remember just to do the top first. So going back to my factoring skills, I want two numbers that when I multiply them, I get a -12, and when I add and subtract them, I get a -4. So playing around with these numbers, I get x plus 2 times x minus 6. If you don't know how to do that very well, you're going to want to make sure you set time aside to come and talk to me a little bit more in depth about how you can jump to factoring your numerators and denominators. Your denominator in this case, since we factored the numerator, our denominator is x squared minus 4. It's the difference of two perfect cubes, so we know we can break this denominator into x plus 2, x minus 2. Because these two main groups are attached through multiplication, I can cross off the two groups that are exactly the same. Therefore, my final answer is x minus 6 all over x minus 2. And again, the x's don't cancel and the 6's and the 2's don't simplify because they are attached through subtraction, both top and bottom, so that is your final answer. Moving on to example 2. Multiplying rational expressions involving monomials. Okay, monomials mean you're dealing with single terms. In this case, we're not adding or subtracting at all. Everything's being multiplied together. So in a situation like this, the easiest thing that I can think of to do is take your numerators and combine them. Since everything is through multiplication, we can actually combine all your terms. And from that point, we can separate them in columns and then simplify according to their terms. So I'm going to actually go through, because they're monomials, which means that they are all single terms, the 5, the x squared, and the y, the 6, the x cubed, and the y squared. I'm going to multiply all of my constants. So the 5 and the 6 up top, 5 times 6 gives me 30. X squared times x cubed, remember same base, we add our exponent, so we get x to the 5th. Y to the first power times y squared is y to the 3rd, all over. Constants 2 times 10 is 20. X to the first times, there's no x over here, so it just says x to the first. Y to the 3rd times y to the first gives you y to the 4th. Because these are monomials, which means it's not adding or subtracting, they're all separate terms, I can separate them in terms of columns. Meaning, I have a constant column here, I have the x's column there, and I have the y column last. So I'm going to separate them just like that. So this can actually be separated as 30 over 20 times x to the 5th over x to the 1st times y to the 3rd over y to the 4th. Go ahead and simplify each of those columns from there. In this case, the zeros cancel out. This is the same as 3 times 10, 2 times 10, so the 10s actually cancel out, so I'm left with 3 halves. Times, if you remember, same base of exponents, you subtract your exponents. X to the 5th minus x to the 1st gives you x to the 4th power. We're going to keep it as over 1 just to keep them balanced. Times 3 minus 4 gives you y to the negative 1 power over 1. Remember your exponents. When you have a negative exponent, that means you flip the whole thing around. So this is the same as 3 halves times x to the 4th over 1 times 1 over y to the 1st power. When you flip those negative exponents around, you no longer have a negative exponent. So if I combine these terms all together, we slap them together, there's no pluses or minuses, my final answer should be 3x to the 4th, that one kind of gets hidden, over 2y. And that's your final answer. Moving on to example 3, multiplying rational expressions involving polynomials. So in this case, we're also multiplying, but here we have not monomials, but we're dealing with pluses and minuses as my terms. So the first thing we're going to do, example 3, we're going to tie into example, the very first example that we did. We want to factor all of our numerators, all of our denominators, and cancel where we can. So we're going to start off with our first numerator, okay? So our first numerator has a 4 in both terms as well as an x. So I can pull a 4x out of my numerator. If I pull a 4x out of my first term, I have the 1 as my placeholder. Minus, if I pull the 4x out of my second term, I have 1 more x left over. All over. Now my denominator, if I factor my denominator out, I need two numbers that multiply to give me 3, -3, and that add or subtract to give me a +2. If I factor this out, I get x plus 3, x minus 1, times, now we're going to move to our second numerator. Factor this out. We need two numbers that when we multiply, we get 6. When we add them, we get +1. So I found I could factor this as x minus 2, x plus 3. And my denominator, 4x, doesn't get any more simpler than that. Okay? Before I move on, I'm going to put parentheses around the rest of my groups. Okay? And the reason I did that is because we're going to talk about this diagonal in just a second, because you can simplify top and bottom, but you can also simplify and cancel on your diagonals. Okay? That's because you're multiplying here. So at this point, again, if you don't know how to factor all that well, now is the time, the next time we meet, to make sure you ask those questions, because the rest of this unit is going to be dealing very closely with knowing how to factor. So at this point, because I have exactly the same 4x and 4x on my diagonals, those can cancel. I can also cancel the x plus 3's on my diagonals. So I'm left with 1, 2, 3 groups. Now before I just call it a day and say that this is my final answer, I also noticed that my top group and my bottom group, so these two groups, my top group and my bottom group, are very similar. They're not exact, but they're very similar. So I'm going to actually go one more step and see if I can simplify or pull out a common number so I can get these two groups to be exactly the same. Because if I can get them to be exactly the same, I can cross more terms out. And the whole point of simplifying is that I want to cancel as many terms out as possible. So starting out, I know that if I pull out a negative number, so if I pull out a -1, these two terms are going to flip in sign. Okay? So down here, if I pull a -1 out from up top, so I'm going to do that over here. So I have 1 minus x. Okay? If I pull a -1 out, then I know that I'm going to have a -1 left back in. If I pull the negative out of the negative x, I'm going to have a positive x. And if you remember, if I just reorganize this, isn't that the same thing as -1 times x minus 1? Those are actually equal to each other. They mean the same thing. And I did that because I wanted my group to match my denominator. So 1 minus x is actually the same thing, just rewritten differently, as -1 times x minus 1 all over x minus 1 times, I still have my group of x minus 2 on top all over 1. Take one more moment to cancel out my two big groups. The -1, just remember, is applied to both of these terms now. Okay? So it's like you're distributing again. And again, if you cancel out everything, the placeholder of 1 is still there. So -1 times x gives me the final answer of -x. -1 times -2 gives me a +2. I have nothing left in my denominator, so that is my final answer. Moving on to example 4, multiplying by a polynomial. So in this case, example 4 is similar to example 3. The only difference is we have a polynomial here where you don't have a denominator. So in this step, example 4, we're actually going to add the over 1 to keep them stacked. Okay? So that's the first thing. So I get x plus 3 over 8x cubed minus 1 times 4x squared plus 2x plus 1 all over 1. They're stacked. That's the first thing, is make sure that they stack. The next thing we want to do is we want to factor every single numerator and denominator as small as we possibly can. So the first thing I'm going to do is I'm going to recognize that x plus 3 is already as small as it can go. Now I can play around with my second numerator, but I'm actually going to tackle this denominator first. I want to factor this denominator first. And we've talked in depth a handful of times already about how to factor the sum or difference of perfect cubes. And the reason we're going to tackle this first is because you're going to see something happen down the road where we'll actually be able to tackle this as a whole group instead of factoring this in a little bit. So if you remind yourself, how do we factor perfect cubes? Well, the first is recognizing you have perfect cubes. An 8 is a perfect cube, an x cubed is a perfect cube, and of course 1 is a perfect cube. So the first thing we're going to do is we're going to write each of these terms before they were cubed. So 8 before it was cubed was 2 to the third power. X cubed before it was cubed, again, was x to the third power, minus, and of course 1 can be written as 1 cubed. So we took each individual term and wrote them as they were before they were cubed. Once you do that, you can circle out your cubes, and you're going to follow the pattern that goes along with adding and subtracting perfect cubes, the sum and difference of perfect cubes. The 2x minus 1 obviously goes into your first parentheses. You have 3 dashes left. This first dash of your second parentheses is always your first term in your first parentheses squared. So 2x squared. We have to square both terms. So 2x squared is 4x squared. Your last term is always your last term in your first parentheses squared. So 1 squared is 1. And your middle is always both of them multiplied together. So 2x times the 1 gives you a positive 2x. If you started off with negative, your first parentheses is always going to be that same symbol. So if it's minus, it's going to be minus here. Your first symbol after your first parentheses is always opposite. So if you start off with negative, that means this first part is going to be positive. And your last term is always positive. So this whole 8x cubed minus 1 can be broken down into 2 separate groups. So this is obviously its own separate thing that we did. So rewriting what we had up here, we get x plus 3 over, I can rewrite this whole cubic difference of perfect cubes as 2 separate groups here. So I get 2x minus 1 times 4x squared plus 2x plus 1 times, my numerator is 4x squared plus 2x plus 1 all over 1. The reason I tackled this first is because what you'll notice is this whole group gets to cancel out. And that's essentially what we wanted, to simplify, to cancel out. So we tackled that first so that whole group would cancel out. If we now push them together, the placeholder, since this whole group is gone, is 1. So I get x plus 3 as my new numerator and 2x minus 1 as my new denominator. At this point, you have 4 now you tries that you can work on. We'll go over these answers together the next time we meet in class. And now we're going to move on to our next video, which is dealing with dividing rational expressions.